Welcome to this course on algebraic geometry and commutative algebra. In the last lecture, we have introduced rings of fractions with respect to a multiplicatively closed set in a given commutative ring. Today, we will see its universal property, which is the most useful property that we will keep using it. So, let us recall the setup. So, we have a ring A. This is a commutative ring, and we have given a multiplicatively closed subset in A, which is multiplicatively closed. That means it is closed under multiplication, and the element 1 is there in S, that is S is a submonoid of the multiplicative monoid of the ring A. So, this is the universal property. Of S inverse A. So, remember that yesterday we constructed a ring S inverse A, and also we have a ring homomorphism from A to this. This we have denoted by iota upper A lower suffix S. But I am going to drop this in when the ring is fixed and the multiplicative closed set is also fixed. We will drop that in the notation, and this map is A going to A over 1, and then this is a ring homomorphism. Alright, so given a ring homomorphism phi from A to B such that the image of S under this phi of S is contained in the units of the ring B. Then there exists a unique ring homomorphism so A is here, B is here, this is the given phi, and this is S inverse A here, this is the iota map. I will call this as simply iota today because A and S is fixed. Then there exists a unique ring homomorphism from this ring S inverse A to B, that I will denote psi such that iota composed psi is given phi equal to psi iota. That means this diagram is commutative, that is the above diagram is commutative. This I will often use, this is often used in commutative algebra as well as algebraic geometry, that given a diagram of arrows, rings or modules, whatever, usually there is one place where you can go to two different places, and wherever a diagram has places where you can go in a different direction, then either direction you go reach the final destination, the result is the same. then you call that a diagram is a commutative diagram. Alright, so now this proof is very easy. So let me indicate the proof. So proof, we want to define psi from this S inverse A to B, and we have given very important property that image of S under phi is a units. All the elements of S here, they go to units here. So S is here, all of them they go to units here. So obviously this condition dictates you how to define psi. So define psi from S inverse A to B by take any element A by S and map it to, where can I map it? So phi of A times phi of S inverse, and this makes sense because phi of S small s, this is an element in B cross, B units. So therefore this makes sense. Now is merely checking. The first thing we need to check that is this map is well defined. That is first thing we want to check, and the next thing we want to check that it is a ring homomorphism, and commutativity of the diagram is apparent because this definition tells you where do A go to. So to check this condition, take any A in A, and I am evaluating iota A. So iota A is A goes under iota to A by 1. This is that iota map, and from here then psi, that is how we have defined here. Where does it go under psi by our definition? That is phi of A and phi 1 inverse, but phi 1 goes to 1. So 1 inverse is 1. So this will go to phi of A. So this definition is actually according to this demand, and now it's only a checking that it is well defined and it's a ring homomorphism. So let us do that very quickly. So first well definedness. So what do you have to check? If I have two A by S and A prime by S prime, then we want to check they go to the same image. Well definedness we have to check always because this is equivalence classes. So it should not depend on the representative of an equivalence class. So what does this mean? This equality means this S prime A minus S A prime and multiplied by some element T in S is 0. So there exists T in S such that this is 0. That is the meaning of these two two pairs A by S and A prime by S prime give the same equivalence class. Alright, and what do you want to prove? We want to prove that where have you defined phi A, phi S inverse. This is what we have defined this, and the other one is phi of A prime, phi of S prime inverse, and we want to check this equality here. So where A prime are arbitrary elements of A and S prime are elements of S. So let us see how do we check this. Alright, so this is 0, that means so that is if and only if T S prime A equal to T S A prime. But once these are equal, then we know when I apply the ring homomorphism phi, apply phi, then what do you get? Phi of T S prime A equal to phi of T S A prime, but it's a ring homomorphism. So this means phi T phi S prime phi A equal to phi T phi S and phi A prime. But then note that this T is in S, therefore phi T by assumption phi T is a B inverse, it is an element in unit group of B, that is the assumption. So I can cancel this element I can cancel, and then this element is also unit, this is also unit in B, this is also unit in B because S and S prime are elements in S. So therefore I can shift it, I can shift this to this side and this to this side, and that is precisely this equality. So that proves that it is well defined. Now we have to prove it is a ring homomorphism. Okay, so first where do 1 go? So 1 is 1 by 1. This is a unit in, this is the multiplicative identity in S inverse A. And where does it go? Under that psi we have defined. This is psi. So that goes to, by definition, psi of 1 by 1 equal to, remember, phi of 1 times phi of 1 inverse. But phi of 1 is 1 itself, so this is equal to 1b actually. Therefore it maps identity to identity. Now we have to check that it is additive and multiplicative. So if where the addition goes, if I have two elements A by S and another one A prime by S prime, this by definition this is S prime A plus S A prime divided by S S prime, and where does it go? Under psi it goes to apply phi to the numerator and apply phi to the denominator and its inverse. So this is phi of S prime A plus S A prime divided by, not divided, so phi of S S prime inverse. Alright, but what do you want to prove this? On one side it goes to this, other side it should have gone to the image of A by S under psi, that is phi A phi S inverse plus phi A prime phi S prime inverse, and we want to check this equality. This is what we want to check, but that is very simple because, alright, so what is this? I will use the fact that it is a ring homomorphism. So this I will expand it. So phi of S prime phi of A plus phi of S phi of A prime and whole thing multiplied by phi S S inverse, and yes, and what is phi of S S? This also I should have written, so I will write it. So this is, first I will expand this and take the inverse. So phi S, oh this is S prime, and the inverse means the inverse will come like this. But now just see that this will get cancelled with this, and what will remain in this, which is this term. So this term will get cancelled with this, and this will remain, that is precisely this term. Similarly When I multiply this by this will get cancelled, this will get cancelled with this, and what remains is this one. So that checks addition. Multiplication is easier. So now for the multiplication we need to prove that psi of a by s times a by s prime, this is equal to psi of a by s times psi of a prime by s prime, but this is what we want to check. But what is this we have defined? This is psi of a prime divided by s prime. That is how multiplication was defined, and this is same as phi of a prime times phi of s prime inverse, which is, because it's a ring homomorphism, it is phi a prime, and this one again like earlier case, this is inverse phi of s prime inverse. And what is this? This we have defined that phi of a, phi of s inverse times phi of a prime, phi of s prime inverse. But you see both are same, this only thing is they have commuted. So this is same, so we have checked this. And again we have while doing the checking we notice that commutativity of the ring is very important. Units? Identity ring also has unit element, that is also very important, we have checked. Alright, now the next step is, so we have the universal property. So one of the important corollary is when A is an integral domain, and S equal to all non-zero elements, which is clearly multiplicatively closed because it is an integral domain. 0 is a prime ideal. So this is multiplicatively closed since 0 is a prime ideal. In general, it is not multiplicatively closed unless 0 is a prime ideal. In fact, that you can take it as one of the definition of a prime ideal. Alright, anyway. So then S inverse A is a field moreover it is the smallest field which contains A, of course as a subring. So therefore S inverse A is called the quotient field of A, or some people also call it field of fractions. Of A. Okay, proof. It immediately follows from the universal property. Let us apply the universal property to the, so take any, first of all S inverse A is a field is clear. Field, since if A by S is an element in S inverse A and A by S is non-zero, which is equivalent to saying A is also non-zero, because this is if this is 0, then that means t times A will be 0. So, if this is 0, t times A for some t in S will be 0, but it is a integral domain. So, there is no 0 divisor. So, A must be non-zero, or t is a non-zero element. So, you can cancel it. So, A must be non-zero. So, A is non-zero, but then the inverse of A by S. So, then S by A makes sense, because allowed denominator allowed is arbitrary element in S. So, this is also in S inverse A, and A by S times S by A, which is AS by SA, which is you can cancel. This is 1 by 1. You can always do that. So, therefore, it is a field we have checked. Now, what does the universal property say? Universal property say that I want to show it is the smallest field. I want to show it is the smallest field. What does smallest means? That means if capital K is a field and if A is contained in K as a ring homomorphism. So, this means A is a subring of K. Then I want to show that this S inverse A is also contained here. This contains here. This map is a injective map because it is an integral domain. This injective, since A is integral domain, because if A goes to 0, where does A go? A goes to A by 1, but if A by 1 is 0, that means some element of S will kill this A. So, that implies there exists S in S with S times A is 0, but S is a non-zero element in an integral domain, therefore, I can cancel it. So, that will prove A is 0. So, that means this map is injective. So, that means A is contained in S inverse A as a subring. Now, I want to show you there is the universal property I want to use to show that there is a map here. This is by universal property. So, to check that, I need to check that all elements of S they are invertible here. So, to check that all elements of S under this map, this is our phi. All elements of S under this map are invertible because this is a injective map. So, non-zero element will go to non-zero element in a field, therefore, it is invertible. Therefore, we know that phi of S is contained in the units of K, because K is a field, every non-zero element is invertible. So, therefore, this is satisfied. Therefore, I can apply universal property, and universal property tells you there exists a unique map here which make this diagram commutative, but note that this is already a field we have checked. This is already field we have checked, and this is a ring homomorphism. So, any ring homomorphism which starts from a field has to be injective, because field has no other ideal than the 0 and the whole ring. Whole thing cannot be in the kernel because 1 goes to 1. Therefore, kernel must be 0. Therefore, it is a injective map, and therefore, this is contained here. So, therefore, this field is contained in this. So, we have checked that any field which contains A also contains S inverse A. Therefore, it is a smallest field which contains A. So, here I have noted something which I want to note it for the future reference. Any ring homomorphism actually one should say every ring homomorphism from a field is always injective. Alright. So, now the next what we want to study is, we want to study now, as I was saying in the last time also, here we have a ring A and given multiplicatively closed set, we have constructed a ring and ring homomorphism S A to S inverse A. And we want to study now the ideal structure of this new ring in terms of the ideal structure of the ring A. Okay, but before I go on, I just forgot to mention that what happens if A is not an integral domain, then what best can you do it? Or what is when A is not integral domain, what is the replacement for the quotient field that will play an important role? So, now A arbitrary ring, and now here you see, in case of integral domain we have inverted every non-zero element, and that didn't cause a problem because A was an integral domain, so the cancellation was allowed. But in general in a ring there may be zero divisors and they will cause problems, but maximum what you can do is you can take S to be the set of all non-zero divisors, the set of all non-zero divisors. In the ring A. And first note that S is multiplicatively close. To check that, we have to check that 1 is in S, which is obvious that 1 is a non-zero divisor in the ring. Of course, we are assuming A is non-zero. So, 1 is not equal to 0. So, 1 is a non-zero divisor, and also we have to check that if I have a non-zero divisor S, non-zero divisor T, then S times T is also non-zero divisor, which is also obvious. Because if S times T is times A is 0, then first use the fact that S is a non-zero divisor, cancel it, and then use the fact that T is a non-zero divisor and cancel it. So, this is also correct. So, we have checked that it is a multiplicatively closed set. Therefore, we can construct this now S inverse A, and now we have this map, and I still claim this, in this case this map is actually injective, because where do A go? A goes to A by 1, and A by 1 is 0 means what? This is 0 means there exists S in S with S times A is 0, but this S is in S which is a non-zero divisor. So, that implies A is 0. So, we have checked this iota map is injective, and this is the maximum possibility. And so, this in this case this ring, this S inverse A has, like in the domain case, S inverse A is a field and it is called a quotient field. So, now this one, this S inverse A in this case is called total quotient ring of A, and that will play an important role, that will play the same role as that of a quotient field when A is an integral domain. Alright, so now we go back to the ideal structure, studying the ideal structures. Studying the ideals, studying the prime ideals, studying the maximal ideals, what happens from A to S inverse A if you go. So, our setup is like this. Oh, before I do that, I will need a concept of a local ring. So, before I start doing the ideal structures of the S inverse A, I want to define. So, definition. So, A is a ring. We say that A is local if there is exactly one maximal ideal. So, if SPM of A is just a singleton, I will call it M, then you call it local. But how do you check there is only one maximal ideal? There is a slightly easier way to check. So, A is local, or let me write in the form SPM A equal to singleton M if and only if A minus the units of A. This is the set of non-units, the set of all non-units in A equal to is a form an ideal in A. That is equivalent to saying there is exactly one maximal ideal. So, let us prove this first. So, proof of this. Okay, so I will prove this way first. This is the set of non-units, but you see I want to prove that there is only one maximal ideal. So, start with any maximal ideal. So, let n be any maximal ideal. So, that by definition maximal ideal does not contain any unit. So, then n is contained in A minus A units, but this is an ideal, this forms an ideal, and this ideal is, once it forms an ideal, it will not be the whole ring. So, this is not, because it does not contain any unit, but this is a maximal ideal and this is not equal, therefore, better be equality here. This is equality. So, it is equality here. So, that means we are starting with any maximal ideal, we proved that maximal ideal has to be this only. So, therefore, it is unique. So, then SPMA is nothing but only the ideal A minus A cross. So, it is singleton. Conversely, I claim, look at this. So, now we are assume that SPM A is singleton. And then what do you want to prove? I want to prove this is an ideal. Alright, this is an ideal and it is a non-unit ideal. This is a non-unit ideal because this is an ideal and it does not contain, no sorry, we want to show that it is an ideal. Look at this set. I want to check that it is an ideal in A. These are all non-units. So, we know that every non-unit is contained in a maximal ideal. This was a corollary to Krull's theorem. Therefore, each one of these elements is contained in some maximal ideal and each maximal ideal is also contained here. So, that means this complement is the union taken over any M is in SPMA. But we are assuming SPMA is singleton. So, this union is only one maximal element. So, this is only one M which is an ideal. So, therefore, we have proved that this is an ideal. So, this is an ideal. So, that proves this equality if and only if statement. It is local if and only if A minus set of units is form an ideal. I must give some examples. So, some examples let us write down quickly. before I close this half example. So, first of all, any field K is a local ring, because 0 is the only maximal ideal. So, SPM of K, which is same thing as a spec of K, which is just singleton 0. Therefore, field is always a local ring. All right, one more example at least, and then if I have a field K, K is a field, and if I take a power series ring in one variable, this is a local ring. Is a local ring with unique maximal ideal M, which is generated by X. This is very easy because we saw in the power series ring the units are precisely all the power series whose constant term is non-zero. So, since I will say since units in this ring are precisely all those power series F such that the constant term, that is f of 0, is non-zero. And there is nothing special about one variable. More generally, K power series in several finitely many variables is a local ring, and the maximum with maximal ideal generated by x1 to xn. Again the same explanation, a power series in several variables is a unit if and only if the constant term of that power series is a non-zero element in the field. And again nothing special about field. So, even more generally, even more, if A is a local ring, A is a local ring with maximal ideal M, then a power series ring over A in one variable or even several variables x1 to xn are also local rings. And what are the maximal ideals? With maximal ideals in this case, take the ideal, so this maximal ideal M of A along with that variable x. This is in this case, and in this case maximal ideal M along with the variables. So, these are the only maximal ideals in these power series rings, and that will also follow from the explanation. If I want to take the units of this ring, I will write several variable case directly. This is precisely all those power series F in several variables with such that f of 0 is belonging to A cross. This is very easy to check. I will not check this, but it is like solving equations, and we do not have to end because we are in a power series case. So, with this I will stop this first half of this lecture, and the next half we will continue our study of ideal structures in a localization. All right, thank you.